3 days ago, the universe blinked, and 25,000 people caught it. Across rooftops, deserts, and silent backyards, a global network of amateur astronomers captured something that shouldn't exist. The clearest, most continuous time-lapse ever recorded of an interstellar visitor, transforming in real time. What they saw broke every rule of celestial mechanics. A tail reversing direction, chemistry that makes no sense, and an object so old it predates the Earth itself. The footage spans 61 days, compressed into 6 haunting seconds. A glowing orb of dust and light, shifting, swelling, flickering like a living thing. It isn't just a comet, it's a time capsule, billions of years old, crossing our solar system for the first and last time. And if calculations hold, it will come closest to Earth on December 19th, just 6 days before Christmas. Scientists are calling it 3I/ATLAS, the third confirmed interstellar object ever detected. At first glance, it looks ordinary, a fuzzy dot surrounded by a pale halo. But this visitor isn't obeying the same laws our solar comets do. It's heating faster, glowing brighter, and changing shape in ways no model predicted. It has survived more than 7 billion years of collisions, cosmic radiation, and gravitational torture, and yet it's still intact. No government telescope caught the full picture. No billion-dollar agency predicted the behavior. Instead, thousands of volunteers with consumer telescopes did. They coordinated across continents, staying awake through storms, through daylight, through time zones, each recording a fragment of history. Now, the combined footage reveals something extraordinary. In the vacuum of space, far beyond Mars, a traveler older than the sun is waking up. What lies beneath its glowing surface? What will happen when it reaches perihelion in 65 days? This is the story of that ancient visitor, and of the people who caught the moment the cosmos blinked. It began on August 29, 2025. California's night sky was cold and perfectly still. Amateur astronomer Vamshi Kassieri sat at his telescope, a faint hum breaking the silence of 3 a.m. The alert tone chimed, a detection notice. He glanced at the screen. Object magnitude 17.8, invisible to the human eye, but unmistakably there. His pulse quickened as he confirmed the coordinates. "I just captured an interstellar visitor," he whispered, not yet realizing he'd started a global relay. Within hours, data rippled through networks worldwide. As dawn washed over California, the sky darkened above Sydney, and Australia's telescopes took over. When they handed off to Europe, the chain continued to South America, Africa, and back to North America again. For the first time in history, a 24-hour relay of citizen astronomers formed a complete circle around the globe, all locked onto one faint smudge of light. Then came the first anomaly. The object's tail, that luminous trail of vapor and dust, was flipping direction. It pointed toward the sun, then away from it, as if confused. Radiation pressure alone couldn't explain it. Mission control centers quietly updated their risk assessments. Something about this visitor wasn't natural. Soon, preliminary data placed its age between 7 and 14 billion years. That's older than Earth, older than the Sun, older than the solar system itself. To the scientists watching the early numbers trickle in, this wasn't just another comet. It was a survivor from before the beginning, a fragment of another star's creation drifting across galaxies. News spread fast. Observatory feeds lit up, and universities issued quick response observation proposals. In a world of billion-dollar instruments and tight scheduling, amateurs had made the biggest find of the decade. By morning, 3I/ATLAS was trending across astronomy forums and science outlets. What began as one man's sleepless night had turned into a planetary effort to decode a visitor from the dawn of time. The amateur time-lapse of 3I/ATLAS covers 61 uninterrupted days, from June 7th to September 6th, 2025. Frame by frame, it shows the coma, the diffuse envelope of gas around the nucleus, expanding from 13,000 kilometers to 26,000. The tail, once a faint thread, unfurls to 56,000 kilometers, 4 Earth diameters across. But numbers alone don't convey what the footage reveals. It's alive with motion, a slow metamorphosis under sunlight. Then came the image that shocked professionals. On July 15th, the Nordic Optical Telescope captured what looked like an anti-tail, a dust plume pointing toward the sun. Radiation should push dust away, not toward it. At first, analysts suspected an imaging artifact. But repeated checks from other observatories confirmed the impossible. The anti-tail was real. In the following weeks, astronomers watched as it curved slowly backward, swinging into the conventional orientation by early September. The explanation was subtle, but profound. Ordinary comets shed microscopic dust grains, easily swept by solar radiation. 3I/ATLAS, however, was releasing massive particles nearly 1/10 of a millimeter wide, 1,000 times heavier than normal comet dust. They moved sluggishly, resisting the sun's push. For weeks, they appeared to form a tail that pointed the wrong way. This unique behavior revealed more than motion. It hinted at structure. The comet's surface wasn't fine powder. It was rocky, perhaps sintered together by eons in deep space, ejecting fragments more like gravel than smoke. To observers, it felt less like watching a comet and more like watching a tiny planet breathe. Dr. Teddy Creta of LOL Observatory replayed the footage 3 times before speaking. "I've tracked comets for a decade," he said. "I've never seen this transition captured with such clarity." His team immediately petitioned for an emergency observation window in December, because whatever was happening, it was accelerating, and the window to understand it was closing fast. On August 6, 2025, the James Webb Space Telescope turned its instruments toward 3I/ATLAS. For 4 hours, it collected the faintest reflections of sunlight from 3.32 astronomical units away. When the spectra appeared on Dr. Martin Cordner's screen, his hands froze. Strong carbon dioxide absorption lines leapt out of the data, but water, the defining signature of every known comet, was nearly absent. He ran the ratio. Then he ran it again. 8 parts carbon dioxide for every 1 part water. It was no computational error. Every calibration check confirmed it. The result stood like a red warning light, an 8:1 CO, 2:H2O ratio, 26 times higher than the solar system average. To grasp the magnitude, imagine a normal comet as a frozen water bottle with a hint of dry ice. 3I/ATLAS is the opposite. Nearly all dry ice, barely any water. Outgassing rates told the same story. Carbon dioxide escaping at 129 kilograms per second, water at only 6.6. Nothing like it had ever been observed. Such a composition shouldn't exist here. Comets formed near our sun carry water, methane, ammonia, not this imbalance. The only places where CO2 dominates are the cold outskirts of carbon-rich stellar nurseries or molecular clouds where oxygen is scarce. Either 3I/ATLAS was born in one of those exotic regions, or something along its voyage fundamentally changed its chemistry. The implications were staggering. This wasn't just another icy wanderer. It was evidence of planetary systems forming under entirely different rules, a relic from a chemical environment alien to anything the solar system had produced. And if its outer shell was so drastically transformed, what might lie deeper inside, preserved since the dawn of the galaxy? Weeks later, the anomalies deepened. On July 20th, spectrographs detected faint nickel emissions from the comet's coma, about 1.8 grams per second, ordinary enough. But when researchers searched for the usual companion element, iron, they found nothing. Nickel and iron are cosmic siblings. They are born together in the same supernovae, condensed side by side in meteorites, bound in alloys across asteroids. Finding one without the other was like discovering a tree that casts no shadow. Still, the data refused to budge. Over the next month, the nickel signal grew stronger, 3.2 grams per second by early August, 4.6 by the end of the month, while iron lines remained absent. In parallel, cyanide emissions spiked. Both elements were increasing in perfect sync, suggesting a linked source within the nucleus. Dr. Bin Yang at Diego Portales University studied the spectra with disbelief. "Nickel without iron?" she muttered. "That's not in any formation model we have." Some proposed exotic condensation processes, where nickel solidified in extreme heat while iron remained gaseous. Others suggested billions of years of selective sublimation. Iron lost first, nickel left behind. But even those explanations strained under the numbers. The data left scientists unsettled. In chemistry, as in cosmology, patterns define truth. Here, the pattern was broken. For the first time, researchers confronted an interstellar object whose metallic fingerprint belonged to nothing known. The more they measured, the more 3I/ATLAS seemed to behave like a relic of another universe's logic. On August 15th, the orbital dynamics team released its trajectory reconstruction. By tracing 3I/ATLAS backward through the galactic plane, they pinpointed its birthplace, the Milky Way's thick disk, nearly 2,000 light-years from its current location. Travel time between 7 and 14 billion years. To visualize that age, consider this. When 3I/ATLAS began its journey, the sun did not exist. The Earth was not yet dust. The entire solar system was still a cloud of gas waiting to collapse. Over eons, the comet endured gravitational tides, stellar flybys, and countless impacts with interstellar debris. By all probability, it should have been shattered long ago. Yet it survived. Radiation from cosmic rays, high-energy protons slamming into its surface at nearly the speed of light, gradually transmuted water ice into carbon dioxide, hardening its crust and tinting it reddish-brown with tholins. The surface became a fossil of radiation chemistry, a record of what happens when matter spends eternity between stars. Dr. Avi Loeb, reviewing the calculations, admitted the object's coherence defied expectation. "It's the oldest interstellar traveler we've ever detected," he wrote, "and somehow it still breathes gas." That paradox is what makes 3I/ATLAS precious. It's not just a visitor, it's a survivor of galactic history, a capsule older than the Milky Way's spiral arms. Every molecule it carries is a signature from a time before our sun lit up. And as it nears the inner solar system, heating and cracking under the sun's light, it's beginning to tell its story, molecule by molecule, photon by photon. The greatest part of this discovery isn't just what we learned, it's who made it possible. The 3I/ATLAS time-lapse wasn't captured by a space agency, but by a global alliance of ordinary people. Teachers, engineers, retirees, students, 25,000 volunteers connected through Unistellar's network, each with a modest telescope and a passion for the sky. Their equipment was humble but powerful, off-the-shelf smart telescopes using high-sensitivity CMOS sensors cooled to eliminate thermal noise. Automated tracking systems kept the faint blur of 3I/ATLAS centered as the Earth rotated beneath them. When California's sky brightened, Australia's darkened. Europe took over next. The coverage never stopped. Every participant collected hundreds of exposures. To build the final sequence, they aligned each frame to the comet's motion, stacking 10 to 20 images per frame to reduce noise. The stars trailed into thin white lines, revealing motion, while the comet remained sharp, a glowing eye suspended in time. The result, 183 frames compressed into 6 seconds that condense 61 days of cosmic evolution. When the render finished on September 7th, someone uploaded it to the network's Discord channel with a simple caption: "We did it." The chat exploded. Messages from Chile, Japan, Germany, and Brazil flooding in. "Science really is for everyone," one user wrote. Professional observatories soon followed. Gemini South's 8-meter mirror in Chile confirmed the tail stretching 56,000 kilometers. JWST delivered precision spectra no amateur could match. But it was the Citizen network that provided continuity, a complete visual diary of transformation, hour by hour, impossible for any single telescope to achieve. What emerged wasn't just a scientific triumph, it was a demonstration of humanity's collective curiosity, a reminder that in the age of automation, discovery still begins with someone looking up. As the news spread through every corner of the scientific community, debates erupted overnight. At the heart of it was one polarizing question: could 3I/ATLAS truly be natural, or were we witnessing something else entirely? Harvard astrophysicist Dr. Avi Loeb had made headlines before, famously arguing that Oumuamua, the first interstellar object ever detected, might have been an engineered probe. So, when he published his July 28th analysis on 3I/ATLAS, claiming its large size and subtle trajectory changes hinted at artificial origin, the internet caught fire again. "It's too big, too stable, and too perfectly reflective," Loeb noted in interviews. "Natural explanations fall short." But science, unlike headlines, corrects itself. On August 7th, the Hubble Space Telescope released refined imagery, reducing the nucleus estimate from 10 kilometers to just over 5. The smaller size meant far less mass, which in turn made natural outgassing forces sufficient to explain the observed acceleration. Still, Loeb doubled down, writing another essay suggesting even smaller objects could be designed for reconnaissance or data transmission. Critics were quick to respond. Dr. Akma Senul-Hake from Petronas University published 2 detailed counterpapers, showing that every anomaly in 3I/ATLAS's motion fell within the statistical noise of sublimation-driven jets, simple sunlight physics, not alien technology. Beyond the noise, the real scientific work continued. 2 main schools of thought formed: radiation processing and exotic formation. The radiation processing camp, led by Dr. Martin Cordner, proposed that 3I/ATLAS's bizarre 8:1 CO2 ratio wasn't a birthmark. It was scar tissue. Over billions of years, relentless galactic cosmic rays had bombarded the comet, splitting molecular bonds, transmuting water into carbon dioxide, and welding its crust into a carbonized shell. The math supported the theory. 7 billion years of cosmic rays equaled roughly 2 × 10 to the 17th power high-energy collisions per square centimeter, more than enough to chemically alter the top 100 meters of ice. Yet their opponents in the exotic formation camp countered with an even more intriguing possibility. What if 3I/ATLAS formed in a star system where chemistry itself was inverted? In certain carbon-rich nebulae, the kind surrounding old red dwarf stars, carbon atoms can outnumber oxygen. There, carbon dioxide can condense as the dominant ice, forming comets that are mirror opposites of ours. To them, 3I/ATLAS wasn't a victim of time. It was a child of an alien nursery. Both sides had compelling arguments, but neither could account for every feature. The radiation theory explained the red, weathered surface, while the exotic formation model explained the bulk chemistry. So a hybrid theory emerged. Perhaps it was both, born carbon-rich and sculpted by radiation into its current form. Now, all eyes turn toward December, because when 3I/ATLAS nears the sun and possibly fractures, we'll see its untouched interior for the first time. If the inside matches the crust, the radiation theory wins. If it's rich in water and metals, the exotic formation camp will be vindicated. If it's something else entirely, the debate will only deepen. The countdown has begun. 65 days until the oldest object humanity has ever studied brushes against the sun. At NASA's Jet Propulsion Laboratory, engineers have reprogrammed antennas in the Deep Space Network to monitor subtle radio reflections from 3I/ATLAS. At ESA, Doppler analysis teams are standing by to refine the object's path with every passing hour. The James Webb Space Telescope has reserved 2 critical windows, one before and one after perihelion, to detect any chemical transformation triggered by extreme heating. Ground-based observatories from Gemini to Subaru are synchronizing their schedules. Even the Vera Rubin Observatory, not yet fully operational, plans to join the watch. And then there's the amateur network, now expanded to 30,000 participants across 62 countries. Discord servers are buzzing with simulation tests, observation schedules, and contingency plans. No one's sleeping through December, one moderator posted. We're catching history live. The stakes are enormous. At 0.8 astronomical units from the sun, solar radiation will be 2.5 times more intense than it is at Earth. For an ancient object already venting gas, that could mean anything from spectacular activity to total collapse. Scientists outline 4 possible outcomes. 1. Smooth passage. The nucleus stays intact, shedding gas and dust but holding structural integrity. In this case, we'll observe stable activity patterns, allowing long-term tracking and rotational studies. It would mean 3I/ATLAS is one of the most resilient objects ever known. 2. Fragmentation. Thermal stress and outgassing create internal cracks. The nucleus splits into 2 to 10 large fragments, revealing pristine interior ices untouched for billions of years. For planetary scientists, this would be a dream. Direct evidence of ancient material frozen before the sun was born. Third outburst. Gas trapped under the crust bursts outward, producing a sudden brightening that could make the comet visible to small telescopes. This scenario would reveal volatile layers hidden beneath the surface, potentially exposing chemicals that no one has ever measured in space. 4. Disintegration. The catastrophic scenario. The entire nucleus breaks apart, dissolving into a debris field that fades from visibility within days. A tragedy to some, a revelation to others. The final chemical signatures would still teach us how interstellar material behaves under lethal heat. Each possibility is extraordinary in its own right, but the one thing scientists agree on is that something will happen. The object's CO2-heavy crust means it's far more volatile than a typical comet. As temperatures rise, sublimation could accelerate exponentially, producing jets powerful enough to spin the nucleus apart. Observers have already begun measuring rotational changes. The current period sits at 9.7 hours, but small fluctuations suggest the spin rate is increasing. If it crosses a critical threshold, centrifugal force could tear the object in half, exactly what doomed Comet C/2019 Y4 Atlas in 2020. For the amateur astronomers, this isn't just science, it's suspense. Every night they check their feeds, frame the coordinates, and wait for the light curve to change. Some stream live images to YouTube. Others log data to open archives so professionals can analyze trends in real time. The collaboration is unprecedented, a fusion of backyard telescopes and billion-dollar observatories all focused on a single ancient speck of ice. By March 2026, after a distant pass by Jupiter, 3 I/ATLAS will be gone forever, flung back into the interstellar void. Humanity will never see it again. One pass, one story, one fleeting chance to watch a billion-year survivor meet the furnace of a new star. 3 I/ATLAS is more than a discovery. It's a bridge between eras, from the birth of galaxies to the modern age of citizen science. It has traveled through darkness older than the Earth itself, only to be seen at last by ordinary people with telescopes on their balconies. Think about that. A 7-billion-year-old traveler, scarred by cosmic radiation, drifting unnoticed across the galaxy, only to be captured not by government telescopes, but by teachers, hobbyists, and students with $5,000 instruments. That's not just science, that's humanity at its best. And yet, despite everything we've learned, questions multiply. Why is the comet dominated by carbon dioxide when every other object nearby is water-rich? Why does it produce nickel but no iron, defying the chemistry of stars themselves? How did it survive unbroken through the gravitational chaos of entire galaxies? We stand on the edge of discovery and uncertainty. In 65 days, sunlight will strike its ancient crust harder than ever before. If it fractures, we'll glimpse matter untouched since before the sun ignited. If it endures, we'll be forced to reconsider what fragility means in cosmic terms. Either way, the data will redefine our understanding of planetary formation across the galaxy. The amateur network isn't stopping. Observation windows are booked. Backup systems are running. For the first time, astronomy isn't gated behind billion-dollar programs or classified projects. It's global, open, and beautifully democratic. Every person who looks up in December will be part of the greatest collective observation in human history. Picture it. 25,000 telescopes across the world, all locked onto the same patch of sky. A single point of light rising before dawn. Chat rooms buzzing in 50 languages as brightness increases. Tails shift and fragments scatter. History won't unfold in laboratories or boardrooms this time. It will unfold in real time, in backyards, on mountain ridges, on laptop screens, as humanity watches an ancient traveler meet the heat of our sun. So, as December nears, set your reminder, follow the data, join the watch, because what happens next will echo across generations. 3 I/ATLAS carries within it the memory of galaxies and the chemistry of forgotten worlds. And when its frozen heart meets sunlight for the first time in 7 billion years, it will whisper the oldest story ever told of what we were before we existed. Until then, stay tuned, stay curious, and keep your eyes on the night sky. Because in just a few weeks, the oldest traveler in the universe will write its final chapter, and you'll be here to witness it.